This video is on how to write ionic and net ionic equations, and how to kind of draw things at molecular level too. So you can draw ionic and net ionic equations for many different equations, but the most common way you're going to do it is with double replacement or double displacement reactions. So here I definitely have a double displacement reaction. I've got a compound plus a compound. I'm going to put in my states of matter. These two are aqueous. All chlorines are aqueous, all potassiums are aqueous. That's not part of the AP rules to know, so they'd have to give you that. I can see my barium is a 2+, chlorine is a 1-, potassium is a 1+, and phosphate's a 3-. So they're going to do some double switcheroo here. Barium is now going to be with phosphate. Barium 2+ is now with phosphate, PO4, which is a 3-. Clearly that's not balanced, so let's put a 3 here and a 2 here. That way things are balanced for the compound. And then we're going to add to that, my potassium is now going to be with chlorine since they switch partners. Potassium is a 1+, chlorine is a 1-, so KCl is all I need. Then I got to think about how I'm going to balance the total equation. That's the coefficients in front. I can see that I happen to have 2 phosphates on the right and then 1 phosphate on the left, so I'm going to need a 2 right here. If I put a 2 right there, I now have 6 potassiums, so I'm going to have to put a 6 right here. Now that I have 6 potassiums, I have 6 chlorines, so I'll need a 3 here, which works out because I have 3 bariums on the other side. I'm going to put a 1 there to just make my life a little easier. Then we got to think about states of matter for the other side. This KCl is going to be aqueous, and my barium phosphate is going to be a solid. So now I'm going to draw each of these things as they kind of mixed. In other words, first I had a pipette or a beaker full of barium chloride, and then I took a beaker full or a pipette full of potassium phosphate, and I mixed the two together to make a new beaker of whatever this looks like. So I'm going to draw what it looks like kind of at the molecular level. Okay, barium chloride. Barium chloride is aqueous, so the bariums have been surrounded by the water. It's a positive cation, so they're going to be surrounded by the oxygens in the water and swoop away from it and dissolve it. And the chlorine is going to be also dissolved, but in this case the hydrogens will point toward it for an ion dipole attraction. I happen to have more than just the 1 chlorine. In fact, I happen to have 6 chlorines. 3 times the 2 makes 6. 1, 2, 3, 4, 5, and 6. And I happen to have 3 bariums here. So I'm going to include that in my picture to have proper ratios. In next beaker over here, I've got potassium and phosphate. Potassium, I happen to have 6 potassiums, K+. And no, they wouldn't all hang out on one side. They'd be going anywhere. And then at the same time I have that, I would have 2 phosphates floating around. Since they're aqueous, they're just surrounded by water and floating around. Now on the right side, after I mix these things together, I can see that I've made a solid, and the solid is going to form a precipitate, which we know to sit at the bottom. And that precipitate is going to be made of my barium phosphate, and I'm going to draw it as it's staying together, because it's not like the ions are floating around separate from each other. It's not like water can surround them and break it apart. So they're going to just sit at the bottom as a precipitate. And while that's doing that, I'm going to also have my potassiums are going to be aqueous. 6 of them. And I have 6 chlorines also. So that's what the beakers are going to look like by keeping proper ratios, kind of looking at volume. You can see that I try to make my volumes additive here for the right product side. So this kind of leads us into an ionic and net ionic equations. Ionic equations are going to show ions, and ions are going to be anything that are aqueous. So anything that you see that's aqueous, you're going to want to split up, just like I did in the picture here. And I see when I split it up, I'll have 3 bariums, 3 barium, 2 pluses, and they're aqueous. And I'll have my 6 chlorines, 6 chlorines, 1-, and they're aqueous. Going on to my next reaction, I've got 6 potassiums. As you can see, I drew that same sort of thing in the beaker. And I'll have my 2 phosphates, which I also drew in the beaker. Going on to the product, so anything that's a solid will stay together in my ionic equations. So I have my barium, phosphate, which will stay together as my solid. And my potassium chloride is aqueous, so it does have to separate. So I'll have to take my 6 Ks, the plus, and my 6 Cls, the 1-, and separate those. So this would be my ionic equation. It shows any of the ions you have. A net ionic equation shows only the things that are even doing anything. In other words, I'm going to take out spectators. I'm going to highlight my spectators in this green here. Spectre ions are the things that do the same on the left and the right. Like if you look at all these chlorines, all the chlorines are just being aqueous. All the chlorines over here on the right are just being aqueous too. They really didn't do anything. So this one here is a spectator ion. It looks the same on both sides. The other thing that looks the same on both sides is your potassiums. They're really not doing anything but floating around before and floating around after. So now to write the net ionic equation, I'm going to take out the spectator ions and only include the things that are doing anything, which is the ones I just circled in black. So my net ionic equation will be barium plus my 2 phosphates to make my solid barium phosphate. So the net ionic equation is what you want to do is start with finding the solid and then just backtrack and find any of the aqueous things that go with it. Hope that helped.